Hi everyone. I'm David. I haven't been teaching for quite a while, so you will have to bear with me. How many of you are biologists here? That's all? All right. We're going to talk today about the digital analysis of microscopy images. That's a title that has been suggested by Ariel. Thank you for inviting me, by the way. And basically, what I do is use AI to monitor cultures and do a lot of things in microscopy. So my company is based on something that I devised when I was still a professor in Jakarta at the university, where I didn't have any equipment, and I started to do AI in microscopy to put some very rudimentary artificial intelligence at that time. I was coding it myself, and that was 9 years ago. And that was for detection of Plasmodium falciparum, the malaria parasite in beet snares. I'll give you an example of this type of technology today. And I thought, because of ParAqua, it's very interesting actually to level up everyone on what deep learning is, how you apply it to the digital analysis of microscopy images, and basically what we do with it with our microfluidics microscope. So getting into it, what is deep learning? Ah, here's what we call the simplistic view. So we got artificial intelligence that spawns that no, it should be green in order to work. Artificial intelligence spawns various things. One of them is vision, and that's definitely interesting us to the microscopy. One of them is robotics, and that's something that is potentially interesting us. Speech to text and text to speech. You had many examples of that. If you got an iPhone, when you say "Hey Siri," that's speech to text. Um, Expert systems, they're pretty much one class where you put anything that you understand. Natural language processing, NLP, that's ChatGPT. Everybody knows about it nowadays. And machine learning, deep learning, supervised, unsupervised, etc. That's one thing that we're going to look into. You will note that machine learning can actually spawn over all of these categories. Now, that classification is a little bit shit for us. Here's one that is way more encompassing about what we do. Artificial intelligence, for me, that's really vision, machine learning, and eventually robotics. And the one thing that is really important and that is never mentioned anywhere is the importance of the context. If you cannot render the context, then pretty much you're doing AI in the void. The context is what brings your AI into production. Example, I can I can take a microscopic image of uh, asbestos fibers and feed it through a model that measures spirulina. And the spirulina model will tell me that there is spirulina in my pictures of asbestos fibers. There's no context. The context is something that you give to the model using metadata. And it's something that we're going to look at. Okay, what is deep learning? Well, deep learning, that's a subset of machine learning and artificial intelligence. Artificial intelligence, you can find many, many definitions for it. But for me, that's really just the effort to automate intellectual tasks normally performed by humans. So that's supposed to be the activities that we are able to carry out that are formalized into and by a computer. Now, that's a very generic definition. Machine learning, funnily enough, when you look for it, it dates back to 2 centuries ago, 1850s. There's two people that were working together. Charles Babbage, that's the not so nice guy here. Charles Babbage decided to make the first computer. His first computer was actually a machine that was making, it was called the difference machine. And it was here to, he never built the machine, but conceptualized it completely. The machine was built in the late 1990s, and it works. And the goal of the machine was to fit polynomials, and to do it way faster than by hand. At the same time, that beautiful lady in the middle is called Ada Lovelace. Ada Lovelace, she revolutionized computer science. She basically is the mother of computer science. She did one thing that was really smart in 1850. She was the daughter of Lord Byron, who was insane, the poet. You know, she walks in beauty like the moon on cloudless climb and starry skies, that sort of things. Now, being the daughter of Byron, who was completely insane, she started to think, wouldn't be, she was a mathematician working with Babbage, and she thought, what would be a set of instructions that would mimic the human mind? How do we organize that? How do we organize the mind in the machine? Which was completely forgotten until 100 years later, Alan Turing, and at the National Physical Laboratory, conceptualized what a modern computer is, where the boundary is between machine and human. There was really, at that time, paradigm shift in the 90s between what we call classical computing and then machine learning. So in classical programming, you take rules, you take data, and you produce answers through a set of instructions, right? This is completely different from machine learning. What we do in machine learning, we take the data, we take the answers. So your data will be, for example, a set of images. You're going to give it a set of answers, saying these images are spirulina, these images are chlorella. And given enough data and enough answers, you're going to churn it through machine learning machine, and it's going to give you a set of weights, and those set of weights, after training, determines the rule. So you're able to replicate that train data into set of rules, which will be, in this case, if you give it new images of either spirulina or chlorella, it will tell you, hey, this is spirulina, I'm sure at 90%. This is chlorella, I'm sure at 98%. So this is what machine learning is. Now, deep learning, go back to previous slide. Deep learning is a subset of machine learning. What this is, it's really actually more a trade name than anything else, unfortunately. Deep learning, it relates to the machine. What is the machine? The machine is a set of logic layers, mathematical operations that apply on very large data sets. Now we're going to go into a little bit more detail Uh, Again, deep learning, deep comes from the depths of the network. We're going to see that. It doesn't come from the fact that it has a deeper understanding of things than human. This is for shit. Now, deep learning. In order to understand what deep learning is, we need to understand two things. Here's an example. That's the hello world of machine learning. That's a digits classifier. It's one of the first useful classifiers that have been put together, and that was put together for the U.S. Postals. For the U.S. Postals, they got 100 people writing some digits. They basically scanned all of this. I think that was done by NIST. Yeah, the data set is called the MNIST. You can download the data set, and the first classifier that you train, that's using MNIST generally, because it's very small, it's very easy to handle. You got images that are 32 pixels by 32 pixels, and you can classify them very easily and test various architectures and ways to behave with that architecture. So what the goal of that classifier is to take your original input, which is a small image, and to produce a final output, which basically is in that range 0 to 9. Okay. If everything goes well, that original input will be classified as a 4. If it goes wrong, it's going to be a 7 or 8 or. Okay. Now, here's the way it works. You got your original input. What layer one does is it's going to analyze features. We're going to find features in every single of these layers. And you can see that those features are going to be abstracted. So we're going to lose information. Layer by layer, you're losing information, or so you think. When you're reaching layer 3, you've got those representations that are no way close to what your original input is. The fact is that connecting this to this to this gives you a very accurate representation of what a 4 is for the computer, right? So sometimes those abstracted layers, they don't seem to contain anything for you, but they've got enough information and trace back to the other layers that they are actually very meaningful to identifying what it is. So this is what deep learning is. Basically, that's a set of abstracted layers, and that's a mathematical framework where you're reducing the problem into subsets that are able to learn the representation of the data. The main interest of this is that this is more than statistics. Statistics, in mathematical sense, that's a Bayesian problem. You wouldn't be able to deal with the amount of data that we feed through a neural network using simple statistics. Okay. Now, how do we do this? We got our set of layers. Now we need to formalize a way to deal with those layers, right? Like I said, a layer is going to be trained. When it's trained, it's going to get weights. What we're looking for is the weights, okay? Now, in order to get those weights, well, what do we need? We've got an input. We get it through this set of layers. We get predictions. The first thing that we're going to need in order to find those weights is to check whether those weights are good or not. So we got our predictions. What if we add the true targets now? If we add the true targets, we can define a loss function. That's basically an error. And from that loss function, there's various ways of defining loss functions. From that loss function, we can get a loss score. And that loss score is how good is my prediction compared to the true target. Okay. So it's going to give me the quality of the network's output, and it allows me to judge it. Okay. Now that we're able to say if this is good or bad, well, it's just a matter of feeding back that information. And that loss score is being fed back to update the weights through an optimizer. And there are various optimizers as well. We don't want to do math. We just want you to understand what the concept is. The concept that is essential here is backpropagation. We take that loss score and we backpropagate through that optimizer to update the weights. One term that you will hear on people that are doing this type of AI is an epoch. What is an epoch? When you take a whole data set and you get it through this operation, when the whole data set has been looked at and you're updating the weights, you've had one epoch. And we're training. We'll see basically we're training anywhere between 15 and hundreds of epochs. The time it takes to compute an epoch gives you the time it takes to train your full network. Okay. So that was all that we had about deep learning. Is that clear? Okay. Let's get into this. How do we apply this new knowledge that we've got? That's one thing that I worked on 8 years ago. Take a thin smear of blood. So basically, you make a blood slide and you stain it using GEMSA and water at the right pH, so that you get the right colors, and you will see your red blood cells. You will eventually see your platelets. So those are clumps of platelets. You will see your white blood cells, WBCs here. You've got various classes of white blood cells. And in oncology, for example, you need to make the slides. And the reason is that you're looking at some abnormals, and you're going to need to scan a lot of slides because, for example, there are very few basophil in blood. So it's a little bit of a pain, and you may want to be able to make your slides and then put them on an automated microscope stage, scan the slides, and pull out only the entities that are interesting for you. Now, the classifiers. Well, what do they all have in common? There's plenty of classifiers, but one thing that they all have in common is that they classify. So at the end, the last layer is what we call a dense layer that will give you the class and the probability. So you can have cats versus dogs, and that will tell you in this picture, there's a cat, and I'm 90% sure. In this picture, there's a dog, and I'm 95% sure. It's been used for fruits. One of the earliest ones that I found was bananas. People were scanning bananas to check that they had the right curvature. Human can be stupid. Fish. That's also an early one where people wanted to determine if fish is fresh or not. Dog breeds. There's a database out there with 100 breeds of dogs. Don't ask me why. White blood cells. this seems to be a little bit a better deal. Here's my data set. So I collected few hundreds of slides. That's easy, actually. You go to an oncologist and you take his box of slides and you scan them, and then after that you do the job. Doing the job, that's you take good pictures and you start cutting from those pictures, and you get your basophils, eosinophils, erythroblast, etc. Ah, yes. Two things important about this. The first one is that your data set should be as homogeneous as possible. So it should be balanced. The second thing that is important is this last line. You can see destroyed cells artifact. Why do we include that? We include that because it's super important when you're doing classification to have a nothing category. So anything that the AI won't understand gets into that nothing category, instead of forcing it into finding something that is not here. It's good to have some crap and to label it as crap. Okay. I know. There's a result. Oh, that one is obviously neutrophil. We get it through our convolutional neural network. And this is the typical answer that you will get. There's a probability that is attached to it. Your neutrophil, it's 95% probability. Okay. So now my output should be a neutrophil. Here's where basically you as a scientist make the difference compared to just a guy that is doing some data through a computer. You need to add the rules at the end. The rules at the end, they're your context. And your context is, man, I've passed 100 slides. I find that eosinophil, 64% confidence level. Yeah, they're good enough to me. I'm making an error of 1, 2, 3 out of 1,000. This is good enough. It won't get better. So those confidence levels, those trust levels, those thresholds, that's basically how you influence the thing. Here's an example. You're getting your errors by class on the test set. We're getting that confusion matrix, actually. I wanted to show you that. That's typically what you get outside of a good network that has been trained. You got the actual versus the predicted, and you should get the highest numbers on the diagonal here, and only a very few errors there. And that's basically your false positives and false negatives. That's where they land. They land outside of there. And in this type of representation, you will very often get some bands here of lighter blue. And that is basically when something on training and validation loss, which I will come back to later, is abnormal. And look, here is your epochs. That's basically your accuracy as a function of the number of epochs trained. Training and validation loss, they should be as close together as can be. So we're going to see that. Now, classifiers, actually, I showed you a little bit about the deep network, but deep neural network, how do they work? Here's a cat. We love cats in AI. Out of this cat, we're going to decompose the picture, and we're going to identify features. All right. So an ear can be an ear, the inside of the ear, but it can be also the contour. We are going to get the nose of the cat. We can get the mouth, etc. What the AI is going to do is combine all those features and re-identify what is an eye, what is what is a nose, what is a mouth, and what is an ear. There's a few properties that are super interesting there. One is that all those classifiers, they are translational invariant, by which I mean, if I move basically the whole face, I'm still going to see it as a cat face. So when you've trained your network, uh, it doesn't matter if something moves a little bit. On classifiers, on objects, that's a little bit different. But on classifiers, it doesn't matter if you move it. Depending on how you train it, they can be invariant to rotation as well. But they will learn spatial hierarchies patterns, which is super important because if you feed it an abnormal with the mouth here and the nose in the middle of the face above the eyes, it will not recognize it as a cat. Trust me on that. So this is hierarchy. They will learn features that are not detectable by a human because we don't care, we don't see them. Typical example is, who's got a cat here? No one? Oh, come on. All right. Does your cat have hair inside his ears? Yeah. Oh, that's good. I noticed that only after training the goddamn thing. So basically, it will grab features like this that you don't really care for. Why am I still here? Oh, there you go. Here's looking at some of those convolutional layers on beautiful kitten. You can see that it will abstract things, and sometimes you will understand it. I understand that these are the contours of the face. I understand that in this layer, it's being able to recognize part of the eyes. And here's one layer fully extracted. If you can find something that relates to a cat here, well, just tell me. I can't. Nevertheless, that's part of the network that lets me recognize a cat with 95% accuracy. Okay. Here's what, before using an object detector, typical workflow looked for me in order to locate, say, a filament or spirulina in a picture. I would take the image, I would extract the luminance channel. So that's basically a variable scale image. I would eventually accumulate images so that I got more contrast, right? Then I would look at the source, do some computer vision on it, like an additive threshold, which gives me a binary image, so black on white pixels. Out of that binary image, I would extract the contours. Out of the contours, I would look at anything that has dimensions that are related to my problem. I would create a bounding bar around that region. I would cut the image. I would put it through a classifier here. And then after that, after classification, I would post-process, parse, text. I would produce the results. Okay. It works. It's a pain, but it works. Now, here's an example. I did it for asbestos. For asbestos, what you want at the end is to take your asbestos fibers. That's a phase contrast microscopy image, by the way. You want to take those little bits, put them through a machine learning model, and it will give you which class this is if you cannot see. In that case, that was straight fibers, which are homocite, curved fibers, glass fibers, peculiar fibers that you cannot classify really, debris and nothing. So that would be typically debris. This here would be typically nothing. Again, you create your class of nothing. That can be the best nothing that I got was a cobweb. Cobweb looks really like some of the asbestos fibers. So you take your data set like this, get those images from your images, and then you got your 5 categories. So this is what you want to recognize. You're going to train the machine learning model. Out of this, with basically splitting the data set into train, validation, and set. Train is what you're going to train the network on. Validation is what is going to feed through your loss function. And test is what you're testing against, actually, that's your ground truth that the model never sees. Okay. Now, you're going to get your weights, you're going to get your model, you can get back to here, and you're solving that problem. There's a much more efficient way of doing this. We're going to see it in a minute. Now, to finish a little bit on classifiers, I need to talk about augmentations. One of the weaknesses for anything that we do in AI is that you need good data and you need lots of it. Okay? You never have enough of it. Trust me. Once you get in bed with a machine learning scientist, the first thing he will request is more data, more data, always more data. So why is that? Well, I just told you, you split your data set into training and validation, and then you're following through the epochs while you're training. You're following whether the training accuracy and the validation accuracy are starting to match. Ideally, they will get close together, and that means that your model is learning. Okay. If they depart from each other, like this or that, that means that the model is not learning. In that case, it is overfitting. What is overfitting? Overfitting is the model is forcing weights onto your data. It cannot learn something. And by learning, here I mean it cannot update its weights in a meaningful way. There are various reasons for it, but generally is that the weights are in local minimum, and there's not enough information to move those weights from a local minimum of the loss to a global minimum of the loss. So not enough data. Now, there's a way to remediate to that not enough data if you think that your data is meaningful. So if you think that you've covered most of the cases and it's just going to be a pain to add more data just for the sake of adding data, you can do data augmentation. Data augmentation, there's various data augmentations that we've got. One of them is adding translations to your images. So you're going to say, hey, I can move that image by 10% to the right, left, top, bottom. And that gives me a new image. I can do scaling. Scaling is dangerous for biologists, depending on what you're doing, really. This one is to take with a lot of precautions, except if you're doing an object detector, because an object detector is scale invariant. You need to know a little bit about this kind of stuff. If you don't, you can always ask me, because I've probably made all the mistakes that you're going to make. So you can shear things. Shearing things, that's basically transforming it like this. And again, this one is very effective if you put only something like 5% shear. and it doesn't denaturate that much. That beautiful kitten. Rotations are the easiest. And rotations, you should always have them in biology because you can rotate anything in microscopy. It will come in various orientations. They're good to have. Mirrors as well. That's basically flipping the image like that, and that would correspond in microscopy to flipping it upside down. So they're not bad to have. Tiling, they're not good to have in classifiers, but I love them here. They're really good to have in object detectors, and they're something that is completely uh, that is completely obvious when you're doing machine learning, and that looks completely stupid when you're a scientist or a biologist or well, anyone who doesn't do it, AI. What you do in tiling is I'm going to cut that picture in four, same thing here, and I'm going to reassemble the tiles randomly. And that corresponds to a sort of drop off that actually really helps with your training and validation loss. So when everything is fine, it looks like this. Your training accuracy and your validation accuracy, they go hand in hand, and the same for training and validation. Okay, so here are a few classifiers. You can build your own convolutional neural network. That's fine. And I would encourage you to build the first one as a hello world example. You really know the tool after that and what to do with it. ResNet, this one is the winner for me. That's a neural network that is included in all the packages. If you got large images, you're going to use large images and a large number of data, you can use a ResNet 101, which is very, very precise. Otherwise, default to the ResNet 50, you will never be completely disappointed. Trust me. Inception, MobileNet, EfficientNet, Inception, MobileNet. I don't see the use for it since ResNet is so good. EfficientNet is a difficult model to implement, but it's actually, as its name says, it's really efficient. It's got one huge interest actually is that it can scale the network. The network will drop the weight that it doesn't need. So it can be if you're tight on space, but we know we never are anymore. It's a good one. Okay, so here's the quick conclusion to this part. We can now classify parts of an image or the whole image, okay? And we still need to pick what to classify, right? It would be cool if we had an AI to do that for us. That's what we call object detectors. So let's look at detectors. I'll tell you straight on, there's two of these five that are implemented nicely and that are easy to use. That's YOLO and the faster RCNN. YOLO is completely open source, faster RCNN as well. Faster RCNN, I think, was devised by Facebook originally. YOLO is actually the state of the art nowadays. YOLO v3, v4, v5. Well, let's look at how it went on. The first YOLO was devised in 2015. I started using it in 2018, so that was 5 years ago with YOLO v3. And then it started to spawn some evolutions. YOLO v5 was the first one actually that used multi-scale resolutions, which was really interesting for what we do in microscopy. And we are currently at YOLO v9, I've only implemented YOLO V8 up to now. That's a very, very strong framework, and there's a lot of commitment about researchers. Now, YOLO, it stands for you only look once, which is completely different from the other networks. The other networks, what they do is they're going to scan an image and they're going to try to find occurrences. Once they found those occurrences, they will rescan where needed. YOLO works differently than this. What it does is it's going to scan the image only once. And out of that image, it's going to give you that ugly thing with a lot of bounding boxes and confidences. And those are predetermined. They're basically what we call anchors. And out of this, and the class probability map, it's going to give you the best match in those bounding boxes. All right. So in principle, it's quite simple. There's one essential complex concept that you got to understand. That's that concept of IOU, intersection over union. What you do is you got a lot of candidate boxes. And out of those candidate boxes, you're going to compute that intersection over union. And that's basically the intersection of these two boxes over the global box. The intersection of our union, the closer the boxes, the IOU, the closer it is to one. Okay. And this is one parameter that you give when you're training your YOLO. Which IOU is your threshold? That's one as well that you get when you're doing the inception. The inception being the detection. Okay. So here's an example of good IOU where we got a dog that is being detected. Okay. And that's done through the non-maximum. That's why I had that slide to remember to talk to you about the non-maximum suppression. The NMS is another parameter, and those are the two that you're balancing. So typically an IOU, you don't want anything less than 0.6. An NMS, you don't want anything less than 0.4. And you should be okay with that, with most of that. How do we train it? So I told you, we're going to take our data set and we'll always partition it into test, train, and val. Okay. Now, the data set is looking at images, and we will have the labels for YOLO that have exactly the same names, but text. And those are the coordinates of your boxes in every single image. Importantly, for YOLO, very importantly, you don't need a nothing class, because anything that has not been labeled as an object is nothing. So it will learn, the YOLO will be really great at detecting nothing. On the other end, if you want to detect something, you got to train for it. So a clump of microalgae, you got to train for it. You've got to include a class of clumps and have enough clumps that they are detected. The way I partition the data set, easily, if you got many images, partition it as 60%, 20%, 20%. 70%, 15%, 15%. For train is always the largest class, right? So training 70%, 15% for testing, 15% for validation. I try to keep those two balanced and to have much more in the training. The size of the data set give you a little bit of guidance. You need to have 15,000 inceptions per class. So that means 15,000 filaments of spirulina that have been tagged, 15,000 chlorella cells that have been labeled. That takes a long time. I'll show you a trick right after to deal with that. You need to have at least 2,000 to get started about anything. So that means that you're going to have to label a lot of data, and the quality of your data set is going to impact your final detection. The saying is garbage in, garbage out. Bad data in, bad model out. Okay, and reminder, check the classification of your boxes and eliminate anything that falls between the classes. Well, you're not sure. Bounding boxes, they've got to be a tight fit to the object. Okay, I won't spend much time on this. You can find this in the notes. The easiest way to get started is if you want to build a model, is actually use one of these online tools like RoboFlow, particularly if you're in academia, it should be free, provided that you share your data, right? And these guys, they will let you label the data using their online tools that are not great but not bad. They will let you import your data. That's fairly intuitive. Actually, after you've done this course, you're able to use that. That's basically where it gets you. You can export your data sets. You can train away from their environment, or you can pay for training inception tokens and train online. The major pain point will always be labeling. And training, it's really become quite easy lately. I can send you instructions actually to do that. There are some other labeling tools, CVAT, which is web-based and free. Label Image, which is not web-based, but which I've tested and works pretty well. I don't know much about the other ones. Once you find one, do that. We have developed as well our own labeling tool that enables basically fast reviewing of data. Here's an example where we were using it to label a data set of rapid diagnostic tests. Here I'm hiding all the classes but the bars, and I want to eliminate the very light ones, which are false positives, which will give me some false positive, and I can check that. So this is basically available on iPad. What I'm doing, no, that one I'll just skip. That one, importing data. So you can import all your data as zip, for example. It's super easy to apply a model to all of them. Here, I'm going to apply a model to one data set that has not been seen. Is just as easy as dropping annotations in, for example. And now I can apply all my annotations to my data. So that's the tricks that we play actually to import, export data outside of the system and get them formatted to become useful. This one I particularly love, and that's basically apply a model to my images. So let's show predictions, and that's useful to label data. What I always say is you start with a small set, you get your first model to work, and then you're able to get the rest of your data, and the rest of your data, use the model that is not super accurate in order to in order to label the things for you. And once you've labeled that thing like that, you can convert your predictions into boxes and use that to retrain. So rinse and repeat, and your data set becomes bigger, it becomes nicer. So you can export data to your format. Okay. Microdits. That's basically where we're going in 10 minutes. Let me show you what this is. I don't recognize all of you. Some of you were in Dubrovnik and they've already seen that. Some of you were not. So there's one machine that belongs to the University of Almeria in Gabriel Lab, and I've brought another one. What we've got here is microfluidic microscope. So we got our condenser, the whole microscope tube fits in that small space, and here we've got a micro channel. So we're able to pump a fluid through that micro channel and observe this. There's plenty of options. We're not interested in this. We're not interested in that. We're interested in seeing it in action, potentially, if that works. Yes. So here I'm pumping spirulina every 1.5 seconds. And what you're seeing here, my red boxes, that's spirulina curve, my blue boxes, that's spirulina straight. And you've just seen a yellow do the inception live. So it's that fast. Once it's trained, basically, we're doing inception on a full image, full resolution in about 17 milliseconds. So it just works. Now, what's important about this system is that we can train it to do anything, to recognize anything. Here's hematococcus that I trained for a customer out of hematococcus solution that I had. It took me 4 hours to label the data set because they're very similar, all that you see. 4 hours to label the data set, 3 hours to train, 7 hours the customer has the model in his machine. Really, you can train anything. And actually, I'm looking forward to going to the lab with you guys so that I can get more data for my personal enjoyment. Ah, still got 4 minutes. That's plenty of time to start addressing ParAqua questions and see what we can do together about this. Paraphysoderma sedebocarense. Does that mean anything to someone? To anyone? Yeah. Antonio, apparently. Yeah. All right. I thought let's do that thought experiment that was before going into Dubrovnik. There, I didn't know what were fungi for. I know very well what are fungi spores that you find in the air because I built a model for this. I didn't think that it would be that different actually for algae. It is because they're very small, they're very tiny. So you've always got to answer those questions before you start building large models, large facilities. Can we see identify parasites? Seeing them, not easy. Identifying them, potentially very difficult. Can we see and identify their effects? Can we maximize the chances to see parasites? And do we have models to find those objects? Okay. Now, in terms of seeing, identifying the parasites, using bright light or dark light, that's going to be difficult. Using phase contrast or DIC, that's probably DIC, differential interference contrast, that's probably going to be easier. Using coloration, night red, if you want to do it continuously, that's going to be a pain. Using fluorescence, potentially, I don't know. That we've got to try. Okay, so it needs to be tested. Now, identifying the effects, that's the easiest approach. Yeah. If you can identify, if you can differentiate a viable cell from a cell that has been parasited, super easy. If the fungi is getting into the cell and you can see purification inside the cell, super easy. That's basically AI will hit that every day because there are different features. There's a different texture. It will do. Okay. So identifying the effects, you can see on your contrast using, for example, just a contrast filter that it just works. Hematococcus, when it's ripe for harvesting, it's full of Isaxanthin. It's basically very red. That's easy to recognize. Okay. Ah, okay. Can we maximize chances? Yes. We're looking at the inside of cells. We can use specific flows. One of the things that is pretty funny is actually that those parasites they stick on one side. They stick basically on the surface. If they stick on the surface, if I give it enough flow rate, basically they will align and they will minimize the drag. The cells will minimize the drag. If the cells minimize the drag, that means that basically I'm going to find a parasite aligned with the flow here or there. So they will rotate. They will rotate on themselves. We've seen that in other problems. Basically, it works. The only problem being that you need to have a very strong flow. A very strong flow means that things are moving fast and it's going to be difficult to capture images. But, we're engineers. Well, I am an engineer, so we find solutions for this. In terms of models, well, we got YOLO. YOLO is really good at a lot of things. It's not so good at determining things that are a huge different range in scale. Now, fortunately, there are some guys nowadays that are working on new models that are enabling you to scan very large image because you want a large resolution to see those very tiny things. Scan a very large image using on every single tile of the image and reassemble those things. So there's solutions that are coming up that should make this thing manageable. The basic problem being that in my testing on spores of fungi, which are about the same range in scale, you don't get better than 50% accuracy on very small particles. But do you need better than 50% accuracy on those very small particles? The laws of large numbers are playing for us. Right? If I measure 100,000 cells, how many do I need to know that my parasites are there? How many are relevant? 10, 20, 100? Very few. So it's just a matter of being able to capture 1 out of 2. I can live with that. I don't know if you can, but I probably could. Okay. So there's a best way for early detection of parasites. And single parasite detection, probably not feasible with the state-of-the-art models and optics that we've got. Finding one every out of 10, that's probably very easy. Much, much easier. We're sure about their effects on the cells, and we're sure that we can detect that very easily, actually. And that means that they've already parasited the cell, and that it's time to act. We're sure as well about the laws of large numbers that are on our side. And we're sure that YOLO can detect those changes, at least at the cell level. Post-processing is potential pathway. You want to do this, basically you need to find a specialist who's able to label your data or infect infect a culture in a small batch size. Don't infect your whole rice weight. Infect a culture, and you got the same culture, you got the infected culture. You can deduct the characteristics of the infected culture. You can mix one and the other to add to your data, which is a very good thing. You capture a large number of samples. You use a PhD student. I'm sorry, guys. You use a PhD student to label the data. You don't want to do that yourself. Train the model. Once you've trained the first model, you loop, get a larger amount of data, refine until you're able to push that thing to production. And I thank you for watching. I'm 4 minutes late.